It's a pleasure to be here today. As Justin mentioned, my name is Kashyap Thimmaraju, and I'm here to present joint work with my colleagues who are all at TU Berlin at one point. So before I begin, I'd like to congratulate the OVS team on winning the SOCER Award. Indeed, OVS is a huge contribution to the SDN community, and I wouldn't be standing here in front of you today if it weren't for them. So apart from presenting the main findings from our paper, I'd like to take this opportunity to talk about how we actually conducted research on this paper. So let's begin. Oops. All right. So in mid-2015, I started my PhD at TU Berlin, and I got to work on a project with the German Ministry for Information Security, also known as the BSI. And the BSI were interested in finding out if they could use SDN to build secure networks in lieu of the Snowden leaks. And so they were concerned about one thing in particular, backdoors. So as the Snowden leaks revealed, the NSA were intercepting shipments of networking equipment to implant hardware backdoors, as you can see in the figure on the left. And then you have state actors like the CIA exploiting zero-day vulnerabilities to control networking equipment as well. So this made us revisit existing attacker models for networking in general and SDN in particular. And so I began my research by investigating what can go wrong if the SDN data plane is malicious, which resulted in a paper at EuroSNP. In short, we identified a new security weakness in SDNs called teleportation, wherein malicious switches can secretly communicate with each other via the centralized control plane, bypassing security mechanisms in the data plane. However, we did not have evidence of an exploit that could be used to create a malicious SDN switch. And so this is like early 2016, and my colleague Bhargava began to dabble in some dynamic program analysis. That's a fancy way of saying fuzzing. And so he had set up American Fuzzy Lop, also known as AFL, in our lab, and was looking for something to fuzz. And so I suggested OVS, as I knew if we find an exploit with OVS, that would justify the attacker model for my research. And so all we had to do was fuzz OVS. And so we also had to think like an attacker trying to launch an attack. And so I had already done some digging and identified the user space packet parsing function of OVS flow extract would be an ideal target as it processes attacker control data. And so all we had to do now was have a test case to test flow extract. And the OVS team had already done a good job of creating a test case for us called test flows. And so we simply had to make a few changes and throw it at AFL and let AFL do its thing. So within a couple of days, we had several crashes. We investigated it and discovered at least 3 unique vulnerabilities reported in 2 CVEs. Thanks, Ben, for looking into them. And so one of the vulnerabilities, oops, oh man. Okay. Didn't expect that. This is the eating up time, sorry. Oh, man. Oh, God. What's happening? I don't see my mouse. Oh my God. Oh yeah, that would be nice.
Okay.
So, or can I just try it one last time?
Yeah, so I think you just drag that one over to your desktop. This is your notes.
Right. All right. So where was I? Yeah, so these were the vulnerabilities. And so we found one vulnerability that gives an attacker remote code execution. And so with this, I knew we had found evidence of how an attacker can create a malicious SDN switch. However, we had only scratched the surface of OVS and were yet to uncover deeper security issues with virtual switches. And so for the remaining time that I have, I'd like to shed some more light on the vulnerability that we found that could lead to a large-scale compromise. After that, we look at 4 of the security weaknesses we identified as part of our security analysis. And then I'll discuss some software countermeasures and conclude and then open up for questions. So back to the RCE vulnerability. So OVS would crash on parsing a long MPLS label stack. So the MPLS header sits between the L2 and L3 header, and you can create what's called a label stack by placing one label in front of the other. You'd use, to indicate the bottom of the label stack, you'd use this S bit to indicate the bottom by setting it to 1. And so if you look at the RFC for MPLS, which is 3032, it states that when you receive an MPLS label packet, simply pop the top label and use that to make a forwarding decision. However, OVS and other virtual switches implement what we call a unified packet parser, where they parse all the packet's headers in one pass and then operate on that rather than the packet itself. So this is helpful for performance. However, there was a programming error in parsing the label stack for the MPLS label stack, so that resulted in a buffer overflow. Let me use the pointer here. So that resulted in overflowing this buffer and smashing the stack for flow extract. And so unfortunately, the default compiled version of OVS with GCC did not insert what's called a canary over the return instruction of the function that calls flow extract. And so this could be overwritten with attacker-controlled data. And so with this, we knew we could use return-oriented programming to create what's called a ROP exploit. And so stack canaries, although could have prevented this and something called position-independent executables, they're not used by default, or at least stack canaries are not present over all functions. And so my colleague Felicitas, who enjoys crafting exploits, spent just a weekend coming up with an exploit. But she had one challenge. Recall processing terminates when the S bit is set to 1. So she had to select gadgets such that the 24th bit of every gadget would be set to 0 until the end of the ROP exploit. And so with that, all we had to do was test it in a real setup. And so to avoid any legal issues, we set up OpenStack Liberty from Mirantis 8.0 in our lab. And that ships with the vulnerable OVS version. And we could go from the VM to the host and compromise that with our exploit. But then when we wanted to go from the compute node host to the controller node, the exploit didn't work. So this is because there's encapsulation, so like VXLAN and VLAN, which increases the packet size. And so we had to slightly modify our exploit by inserting what's called a NOP slay. So just a bunch of no-op instructions so that we could overcome the increased packet size. And so once we had that, we could then control or compromise the host on the controller node. And then from there, due to the centralized nature of OpenStack, we could spread to all the other nodes in the cloud. And so now that we've seen how a worm can manifest in an SDN-based cloud, I'd like to tell you why this was even possible, which brings me to the security analysis my colleague and I conducted. So we identified 4 key issues with virtual switches, the first of which is the unified packet parser, which is a centralized parser that I alluded to earlier. And then, like Justin mentioned, implementing parsers for these protocols can be error-prone. And correct me if I'm wrong, all the implementation for the parsers has been done manually, not automatically. And so here's a long list of all the supported protocols by Open vSwitch. And we also look at how these supported protocols are growing over time. So on the x-axis, you have the time. Then the green diamond is OVS. And the gray star is Cisco Nexus 1000V. And on the y-axis, you have the number of parsed protocols. So you can clearly see it's going up. Maybe it's not growing really fast, but it's growing up slowly. And so with every new protocol you introduce the chance of a vulnerability. Next, we have the fact that the virtual switch processes attacker-controlled data. And so one could argue that you have IP tables and the kernel to filter things out. However, as we saw, if there's a vulnerability in MPLS, that's not caught by IP tables or the kernel. And so IP tables and kernel sanitization is also rather limited to a few fields in the IP and TCP header. Another critical weakness we observed is the fact that the virtual switch is co-located with the host OS, or the virtualization layer in general. So once an attacker compromises the virtual switch, she also compromises the host OS as well. And finally, we have centralized control, a key tenet of SDN. And so all the virtual switches are connected to a centralized controller. And so once an attacker compromises the virtual switch, she can easily spread to the controller, and from there on to all the other nodes in the cloud. And so to summarize and put this into perspective, an attacker with limited resources can easily rent a VM in the cloud, and to launch an attack, she can target the unified packet parser of the virtual switch. Due to co-location, she can compromise the virtual switch and break out of isolation by owning the host. And due to the centralized nature, she can go from the compute node to the controller node, and from there on to all the other nodes in the cloud. And so the natural next step for us was to look at mitigations. And so from a software security perspective, we have protections in user space and in kernel. So there's the fast path, which is kernel space packet processing, and then you have packet processing also in the user space, and we need to protect both of them. And so like I mentioned, we have stack canaries and position-independent executables, and we have address space layout randomization as well. At the kernel, we have what's called GRSec security patches, which also protect against memory corruption issues and ROP exploits. However, this is specific to the Linux kernel, but it's still worth using depending on the use case. So we'll look at that in the performance evaluation. And so by using these countermeasures, it introduces the classic question of trading performance for security. And so we conducted a performance evaluation of the user space and kernel countermeasures to see what impact it has on the forwarding performance of OVS. And so we looked at using stack canaries and position-independent executables in user space and the GRSec patches for the kernel. And so we set up a server running OVS with a single forwarding rule, so input 1, output 2, and then had a packet generator send a bunch of UDP packets through OVS to the sink. And then using passive network taps on those links, we collected the packets at the monitor, and using hardware timestamps, we could accurately and precisely see when the packets arrived and got forwarded to then calculate the throughput and latency. And so we had OVS set in 4 different settings. So we had the vanilla, the default system, so no countermeasures in user space or kernel. And then we had user space countermeasures only. Then no user space, but patch the kernel with GRSec, and then GRSec patch plus user space countermeasures. So let's look at the results. In the slow path, this is when all packets go through the slow path. So this is not something we'd expect in a real-world setup where all packets go through user space. But this is sort of like a boundary condition, and we wanted to see what the overhead for user space countermeasures would be. And so on the x-axis, you have packets per second sent. And on the y-axis, we have packet loss in percentage. The green diamonds are vanilla default. The blue star would be user space countermeasures only. The gray circle is GRSec only. And then the red triangle is GRSec and user space countermeasures. So clearly, we can see that all the countermeasures introduce some overhead. And the overhead for user space only is about 13%, whereas GRSec and user space is about 27%. So that's quite a big hit. However, the user space countermeasure, 13% it's not so big for all packets going through user space. And since we don't expect that, I don't think it's all that much. However, the kernel space countermeasures it depends on the use case, I'd say, adopting it. And so if we look at the fast path, we can clearly see user space countermeasures don't have an impact, because if they did, then something would be wrong, because all packets are only going through the kernel. But what's very clear is the max throughput on our system without kernel countermeasures was about 700 kbps, whereas with GRSec, we can go only at about half, so 350 kbps. And so adopting GRSec in the real world where you want high throughput would be questionable. So to summarize, the user space countermeasures introduce small overheads and must be adopted, whereas the kernel countermeasures introduce a considerable overhead, and its adoption really depends on the use case. And so with that, I'd like to conclude and say that we looked at 4 security weaknesses that could lead to a large-scale compromise. So namely, the unified packet parser, the fact that the vSwitch processes attacker-controlled data, and then we have co-location of the vSwitch with the host OS, and centralized control. And then we looked at some mitigations for user space and kernel. User space countermeasures like unconditional stack canaries and position-independent executables must be used by default. However, the use of kernel countermeasures really depends on the use case. And if you want more details, please have a look at the paper. With that, thank you for your attention.